Welcome to Watch Mojo, and today we're counting down our picks for the top
5 calculus topics. That was a seamless transition right there. Please note that these are not ranked because why would you do that? Why would you rank calculus topics? Why? They're just in the order you'd learn them in. So, number 1, limits. So if you were a calculus newbie and I had to explain limits to you because I had been tasked to do that by somebody, first off, what were you thinking asking me to explain calculus to somebody? But second, I would say that a limit is basically like what a point looks like it should be. So let's say, for example, you had this unassuming looking parabola here. Well, surprise, it's weird because in this hypothetical scenario, right here, at this point, you have to divide by 0. So that point now doesn't exist. That point is nothing. You plug that point into your calculator, you get error because it doesn't exist. But it still has a limit. So to explain this, I'm going to need to pull out the handy zoom backgrounds. Oh, wait, wrong one. Okay, give me like 5 seconds. Okay, almost. Gotta add it. Okay, we're almost there. Just bear with me. Come on. Like, give me like 5 seconds, and there we are. Okay, all right. We got this good old parabola right here. It's there goes my hand. It comes along, right? Like following this parabola, but right here, as I said in the hypothetical right now, it doesn't exist. But it still has a limit there because it looks like it hits 0. And so that means it's approaching, the closer it gets to that point, 0 on the x-axis, the closer it gets to 0 on the y-axis, but never actually hits it because that point, 0 on the x-axis, doesn't exist. But that means since it's approaching that, the limit of 0 on the x-axis is 0 on the y-axis. Also, sometimes a function doesn't just have a limit. Like, where's the limit here? Like, it's got a completely separate limit coming from the left than the limit coming from the right. Like, math. Number 2, differentiation, or as some people call it, most people, derivatives. So on the screen here is the derivative formula. Now, if you plug a function into this formula, you'll get its derivative. But what does that mean? Well, I can answer that right here. Once you have put your function, f of x, through this function, you'll have f prime of x, or the derivative of f of x. Now, that function is also a function of x. I think I'm doing this quick. But comment if I'm wrong. When you plug a number into f prime of x, you get the slope of a line that is tangent to the point at the same x-coordinate on f of x. You can use that to find rates of change of one variable with respect to another variable. Number 3 on my list is a continuation of number 2. Number 3 is the rules that make differentiation easier. There's a good number of these, so I'm going to go over them fairly quickly. The constant rule is that the derivative of any constant is 0, whether that constant is 7, -3, 1,000, also 0, no matter what it is, it'll be 0. The power rule states that if n is a rational number, then the function f of x equals x to the nth power is differentiable, and the derivative of x to the nth power is nx to the power of n minus 1. So basically, what that means is, let's say you have x squared. You take the thing that's in the power place, the 2, you move it to the front, so now it's 2x, and then the power is what the power was, but minus 1, so 2 minus 1 is 1. So the derivative of x squared is 2x. The product rule states that the derivative of the product of two functions is the derivative of the first function times the second function plus the derivative of the second function times the first function. The quotient rule states that the derivative of f of x over g of x will be g of x times f prime of x minus f of x times g prime of x, and then divide all that by g of x squared. And there's also the chain rule, but we don't have time for that because, the video can't be too long, else no one will want to watch it. I mean, no one's probably going to want to watch a calculus video anyway, but, number 4. Integration. Let me just consult my book since it's been a while since I've been in class. Oh, I'm already there. Wow, would you look at that? Okay, so integration. Not there. Got it, okay. Integration is the opposite of differentiation. So basically how addition has its opposite in subtraction, multiplication has its opposite in division, exponents have their opposite in roots, whatever you know what I'm talking about. That's gonna bug me. What is that called? Radicals, which, to be honest, I didn't remember that. But I digress. We were talking about integration. So integration, opposite of differentiation. When you integrate something, you're basically finding a function that the function you started with would be a derivative of. So, for example, in the example I did earlier where we differentiated x squared to 2x, 2x integrated would be x squared, except there's a catch, because any constant becomes 0, then we don't know what constant may have been tacked onto x squared. So the integral, is it integral? Is that what it is? Is that the term? Integral. We're going with integral. I'm going to Google search it. Integral. I was right. Okay. Was I? The integral of 2x would be x squared plus c, because it could be any constant that could be there when we differentiate it, because, it came from 0, like it could have been anything before that. So, yeah, that's, now it's kind of awkward. And finally, number 5, which I don't have a catchy title for, but it's one of the applications of integration. So using integration, you can find the area of a region between two functions. Throw that book aside. Basically, using... I might need that book actually. One of the things you can do with definite integrals is find the area of the space under a curve. But you can extrapolate upon that, and why did I say extrapolate? I just want to show off my vocabulary at this point. There is literally no reason for me to say that. You can use that to find the area between two curves, because you take the area of the top curve and subtract the area of the bottom curve, and you'll have the area in the middle right there. Not only that, but with methods called the disk and washer methods, you can further move that on to solids in 3D space. There's a couple different methods for that, which I just mentioned. But yeah, that's the top 5 calculus topics. It is 9:22 currently, so I'm gonna take a be a blooper reel if you want to see me make fun of myself for, well, not really make fun of myself, more act stupid in front of the camera for 1 minute and 17 seconds more. So yeah, hope I get a good grade. So this function, it's coming along. Ah, there goes everything. It's coming along like this. You see, here's the function. Ooh, I can't follow that. And it's. Let me get out of the shot. Function is coming along like this. And right when it hits like there, you see, right, it doesn't, whoa. Let's try that again. All right. Let's see, function's coming along like this, right? Here it comes. Okay, scrap that. Bear with me. Alright, I got this, okay. Function's coming along, right? Here it is. It's like there, and it gets down to like right where I'm blocking it, right? Whoa. We're gonna need to cut some of this out. Like there's a little too much.